Hi guys, let's talk about series circuits. You definitely want to watch this after you've watched the current, voltage, resistance, and intro to circuits video and the circuit diagrams video. So if you haven't seen those yet, go back, watch those first, and then come back to this one. A series circuit is a specific type of circuit where all current flows in a single path. So if you look at the picture down here at the bottom, notice that there's only one possible path to get from one side of the battery to the other, right? So let's say that we're talking conventional current and our little charges are going to flow this way. There's only one possible way to start from over here and end up over here, right? All of the current has to travel through all three resistors. If there's any kind of an issue at all in the line, then the current won't make it. So that's kind of a hallmark of series circuits. That's the idea that if, let's say that this light bulb right here goes out, the rest of them will not light up, and the reason is that now there's no path from this side of the battery to this side. There's no way to get across that, if you will. Series circuits are that you might be familiar with would be like the annoying Christmas lights where one goes out and the whole string is dead. You got to find the one that's out to fix it. That's probably the best example in life that I can give you. Okay, so because all current flows in a single path, that means that current is the same at all points. Current is the same everywhere. So if I were to take a little tool called an ammeter and measure current, the current would be the same here, it'd be the same here, it'd be the same here, it'd be the same here. It doesn't matter at all where you're measuring, current is the same. If it helps, you can kind of think of electrons or charges as cars, and the path is the road. So with a series circuit, there's only one road. All the cars have to travel on that road. They're all going to be backed up equally by the amount of wrecks or construction or whatever is on the road. And so the reason for that, again, is that there's only one possible way to get from point A to point B. There are no shortcuts. There's no detour. There's no way to get around any kind of an issue. Okay, so current is the same everywhere. And on that note, resistances, those are going to be our wrecks or construction areas on the road. Those build up. So if I come across this first wreck in my car, and down the road there's a second wreck and a third wreck, all of those are going to back up the traffic more and more and more and more. Okay, so resistances add up. We call total resistance equivalent resistance, and so that's something you want to recognize anytime you see RT or you see a problem refer to equivalent resistance. Know that that is the same thing as total resistance. And in series, all resistances add up. Okay, so we have an equation for that. It says equivalent resistance here is equal to R1 plus R2 plus R3 plus however many there are. You adjust that equation to show how many resistors are actually in the circuit. Moving forward, since current is the same everywhere, we can use Ohm's law to calculate it. But again, because the current or the flow of traffic is affected by all of the wrecks on the road, all of the resistance, we want to make sure that when we use this equation, we're doing RT or equivalent resistance on the bottom. In series, never find current using just a single resistor, because that will not be the true current. Current is affected by all resistances all the time, so you have to use RT in the formula. The third formula that you can see down here at the bottom indicates that the voltage is actually going to be split up amongst all the resistors. So V1 would be voltage for resistor 1, V2 would be voltage for resistor 2, V3 is voltage for resistor 3, etc. If you added all those up, then that would equal the total, which would be the battery or the outlet or whatever voltage source you were given. So let's take a look at how we can have different voltages. This is something called voltage drop, and it's a little bit weird, but let's say that, again, we're going to talk as if we're doing conventional current here. So you've got a little charge, and it's trying to move from the positive side of the battery here over to the negative. There's a difference, right, between positive and negative. So this little charge has lots of energy. It's motivated to move. It doesn't want to be near the positive, and it wants to get to the negative. Okay, so it's going to cruise around with that total amount of voltage, and then it's going to come upon a pothole. It's going to struggle to get through that pothole, and so because it is struggling, it's working hard to go through the resistor, or the pothole in this example, it's going to use up a little bit of energy. And so we can actually measure that. We call that V1, and it was the amount of voltage used across resistor 1. Okay, so because some of it was used up, that means there's a little bit less for R2. It's going to struggle through R2. Maybe there's a fender bender here, so this little charge is struggling. It's got a little less energy to begin with. It's hit another resistor. It's going to drop more energy, which means it's even lower by the time it gets to R3. Well, R3 is the toughest one of them all, and by the time it gets across that, it's got zero energy left. Okay, so it can still actually cruise around to get to the negative, but we would say down here is 0 volts because all of the voltage has been expended on those resistors. And let's say this was maybe a 9-volt battery. If we measured with a voltmeter, we would get 9 volts over here and 0 volts down here. Okay, so this is a phenomenon called voltage drop. We do have an equation for that, which is this one. V sub n equals I times R sub n. So the I, of course, is current. The N just stands for this specific resistor. So if you want to find the voltage drop or the voltage used by resistor 1, you would call that V1 and R1. Okay, if you want to find voltage over resistor 2, you're going to call that V2 equals I times R2, and so on. Okay, so we can find the voltage drop by using this equation, and then if we go back and look at the slide before, we're going to use those voltage drop amounts that were here to find the total if it wasn't given. Alright, so let's apply all that. So first step here, a series circuit has 3 resistors of 2 ohms, 4 ohms, and 16 ohms, and a voltage of 24 volts. We want to start with a drawing. It's important in series to make sure that you only have one possible path to make it all the way around from one side of the battery to the other. And so basically that means these are always going to look like a box. Okay, and then it's helpful to go ahead and label these. So I had 24 volts for my battery. I've got resistor 1 of 2 ohms. I have resistor 2 of 4 ohms. And I have resistor 3 of 16 ohms. So the picture is helpful for a number of reasons. One of them is that it's really nice to be able to just look at the picture real quick and see what I'm looking for instead of having to scan through the problem and choose the numbers that I need. Secondly, I can figure out exactly where the problem is talking about with a visual. Okay, so we've drawn the circuit. Now we want to find the total resistance. If you look at your formula sheet, total resistance or equivalent resistance in series is where you just add up all those resistors. So we've got 3. We're going to say R1 plus R2 plus R3. And so R1 was 2 ohms, R2 was 4 ohms, and R3 was 16 ohms. So 2 plus 4 is 6, plus 16 is 22 ohms total. Alright, next step, find the total current. So again, I'm going to look at my formulas on the series part of the formula sheet. It says I is equal to V over RT. Well, V was given as 24 volts. And RT I just found was 22 ohms. Remember, on finding total current in series, it's really important to always use only the RT. So 24 divided by 22 is 1.09 amps. And that is my answer here for I. If I was to take an ammeter and measure the current here, I'd get 1.09 amps. If I was to measure the current here, I'd get 1.09 amps. You can see what's going on here. The pattern is that current is the same everywhere throughout the problem. Okay, last step. Find the voltage drop across each resistor. So the basic equation for voltage drop was Vn equals I times Rn. The n's again refer to the specific resistor. So when we find voltage drop for the first resistor, we're going to say V1 equals I times R1. I we just found to be 1.09. Can't get a decimal here. There we go. Times R1 was 2 ohms, and that is equal to 2.18 volts. So that is V1, voltage drop across resistor 1. If I took a little voltmeter up here and measured the voltage, I would find it to be 2.18 volts. Okay, V2 is going to be I times R2, so that will equal 1.09 times 4 ohms, or R2. V2 is equal to 4.36 volts. So if I took a voltmeter and I measured across this resistor, I get 4.36 volts. And then last but not least, I'm going to erase my original equation here so I have a little more space. I've got V3 equals I times R3. So V3 will be 1.09 times 16 ohms. And that gives me a voltage drop 3 of 17.45 volts. So again, if I was going to take a voltmeter and measure right here, I'd end up with 17.45 volts. Now all of those I rounded a little bit, but if you add up 2.18 plus 4.36 plus 17.45, it should be approximately 24 volts. That's one way to check yourself to see if you did voltage drop correctly or not. And that's it for series circuits.